And tell it I don't want to see the subtitles. All right. So questions about project 6?
I might reiterate my question so the recording can have it, but
Yeah.
I'm also trying to find a way to vocalize my question properly. Within the memcopy program, we have to calculate how many times we chunk up the amount of bytes by 32, and then we have a remainder of that 32, which we have to also copy over. What I'm basically trying to go with, did I do my math correctly? Because it is a bit difficult for me to tell if I did my math right.
Okay.
And
Well,
I'll probably
to debug that, you'll want to work out with pencil and paper what the answers should be for a given size, then test and make sure that the answers are what you expected them to be. Okay, so tell you what.
So, yeah, I know, it is hard to.
Cephas, you're
Please,
unmuted.
can you mute yourself, please? All right, so, oh yeah, I rebooted, so I need to start up QuickTime again.
If we have time, can we go over loop unrolling a little bit? Because I know I was struggling on that on project 5, and I know it's in project 6 as well.
Yeah, but you're told how many times to unroll the loop, so, and that's 8.
As a concept, I don't really
Yeah.
understand.
Okay, so let's try let's try 3 different sizes, okay? Okay, so let's try one. Let's start out with, okay, so somehow you're told that the size is 350. Okay, so you want to know how many 32s. Okay, that's going to be 10. 10 times 32 is 320. So 350 minus 320 is going to be 30.
Are you supposed to be sharing your screen, or are you just drawing
I'm
on
not.
pen and paper?
I'm not. Sorry. I thought I was. Well, I was certain that I was. Okay. All right. So I'm going to back up. All right. So you can transfer 10 32s. I don't know whether to put the. Now you've got transfer of 32s unrolled 8 times. So let's rewrite 10. 10 equals 8 plus 2. So you have an unrolled loop here. So top colon, and then there's a transfer 1, 2, 3, 4, 5, 6, 7, 8. So you'll start with the remainder first. So if you enter here, do 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10. And now you're done with 32s. There can't be any more 32s left. Because if there were, you would have done them by now.
So
So,
I
yeah.
have a, so could we do it where we use the eight, but the normal eight,
On Thursday.
what is it, the Duff device for 8 bytes?
That's a
Well,
little nerve-wracking.
yeah, eight bits, I
Okay,
guess.
Mama.
And then so we know we can figure out how many 32s we have to do, but we do the extra bits first to get all the stuff normally, and then the rest of it we transfer 32 bytes at a time. You get what I'm saying?
Yeah, and that's not going to work.
Why would it not work?
Because let's say you have an odd number of bytes left over, which you do first. That means you're starting out your transfer of 32s in an odd address.
Why
What?
would it? I don't see why you would be
All right,
transferring
see
it.
this. So you want to transfer 33 bytes. You say do the first byte first.
Mm-hmm.
Okay, so you transferred 1 byte. Where's your starting address now?
Supposed to be this place. So why would that not be legal?
Because if you're going to transfer 32 bytes at a time or 16 bytes at a time or whatever, it can't start on an odd address. There's alignment issues.
So why can you transfer 1 byte, 1
Because
bit,
one
I
is
guess?
special.
Huh. So you have to transfer the 32s and then do the rest of them.
By transferring the 32s first, and you started with memory that was aligned with the 16 byte boundary, you're guaranteed that you're starting at a good alignment, and you're guaranteed that a 32 byte alignment is. All right, say it again. You know that your memory started out as being properly aligned. You know that 32s are properly aligned. So you take care of that, and then whatever's left over, you take care of with specialized instructions. Okay, so specialized instructions, for example, you know, what are we talking about for specialized instructions? The kinds of transfers you're going to be doing in this program, there's going to be the LDP, an STP into Q0, Q1, doesn't have to be 0 and 1, from a source register, advanced by 32, Q0, Q1, to a destination register, advanced by 32. So there's one kind of set of instructions. Then when you are done with your 32s, there aren't any 32s left. Whatever remains must be less than 32. So what could it possibly be? Maybe there's a 16. So that would be LDR with 1 Q register. Maybe there's an 8 left. That would be an LDR with an X register. LDR meaning load and store pair. Maybe there's a 4 left. So that would be with a W register. Maybe there's a 2 left. That would be a W register and an LDRH for half of a W. Maybe there's 1 byte left. LDRB with a W register.
So why don't we just transfer like all of the rest of them 1 byte at a time? I mean, I guess it
It's
would be
slow.
marginally slower. Yeah, but if you think about it, if you're having a bunch of bytes, 32 extra ones is almost negligible for actual performance time.
Okay, well, you got that. Yeah, that's fine.
They don't have to do all this mess.
Well, this mess is not any more or less of a problem than transferring less than 32 bytes but one at a time.
Well, it would be like, because the other one you'd have to do a bunch of mod checks and then,
No, there would be bit tests.
well, you have to do a bunch of tests. Yeah, like you'd have to somehow mod or get if it's divisible by 8 or 4 or 2 or 16 or whatever.
Right. Okay, well, I will readily grant that if the a loop done inefficiently is still a negligible contribution to the overall execution time because you're guaranteed to be transferring at most 31 bytes. If it were 32, you would have taken care of it already. All right, so if you want to transfer the last 31 bytes, up to 31 bytes using a loop, 1 byte at a time, knock yourself out.
Okay, that was my plan.
Okay. Does that include knocking yourself out?
Yes.
Okay, good. I'm happy. All right. Any other questions about project 6? All right, well, let me finish up my example then. Okay, so we're doing 350 bytes. How many 32s can you do? Well, that is 350 integer divide by 32, you get an answer of 10. 10 is itself made up of 8 plus 2. You start out with the 2. This is the jump table duff device part of the project. So if your remainder here is given your remainder of the 32s, you want to, if your remainder was 0, jump here. If it was 7, 6, 5, 4, 3, 2, 1. So if your remainder is a 2, you want to jump here. Do 1, 2, then you loop back and do all 8. Now you've got 8 plus 2 is 10. You're done with your 32s. Then transfer the remaining bytes however you want.
Okay, so I emailed you about this. I understand this logic, and I have the code that should be working. But when I try to manipulate the BR, so it's displaced by X amount of bytes into this selection thing, it doesn't work. Because we know that LDP plus the STP is going to take 8, since they're both 32 bit
Right?
instructions. So if you add 8 to whatever you get for the base register or the location of the label, then you should be able to skip 8 times some number, whatever your modulo is. Then you have to subtract it from 8 or whatever, and then you'll get there. But it never works. It always goes to the top for me. And I don't know
Okay.
why.
Well, can you make an appointment with me and we'll investigate together?
Okay.
Okay.
Is anyone else having that issue, or is it all hunky dory?
Okay. So let's put a period on this. So your remainder is 2, right? So how do you figure out how to get here? Well, 2, right? Take away 2 from 8. So 8 minus the remainder is 6. 6 times 8 is 48. Given that if you imagine that this is byte 0, then if this is byte 0, then this pair of load store is going to begin at 8. This pair is at 16. This pair is at 24. This pair is at 32. This pair is, am I doing it wrong? 8, 6, Okay, so this pair would be 40, and then this pair is 48. There's 48, 48. See how it works?
It's making more sense.
I've just needed this concept explained again and again, because like it's not sticking, but it's getting easier and easier each time.
Okay.
It's said.
Okay, what year are you in now, Rebecca?
Sophomore?
Okay, so should I check back with you when you're finishing junior?
A lot of us are sophomores, I think.
Okay. All right, well, it's now explained a number of times on the videos, so you have the opportunity to hear it again and again.
Does anyone?
And if you want to hear me do it again and again, make an appointment with me. I'll be happy to do it again with you. And you
Does
know
anyone
what?
have this bit implemented? Oh, sorry. You can continue. I'll shut up.
All right, so Cephas, if you want to ask a question, perhaps do it when I'm not in the middle of a sentence. So if you want, you can get together with a couple of people and book up a single appointment with me, and I can help several of you at once. All right, either way, if you want help, I'm here. Okay, Cephas, your question.
Does anyone have this part actually implemented?
The part where it's like they jump in the middle of a loop.
Yeah, and
I-
you know that it's implemented correctly.
Yeah, I got it working.
I just
So, so are you doing a move PC and then giving it a register? Because that does not work anymore.
No, that was only for ARM v7.
Yeah. Okay.
Yeah,
'Cause I
that
was doing that
instruction, as Jordan knows now, that instruction does not exist in ARM v8.
wait. What command?
Prior to ARM v8, there was an ARM instruction that would modify the program counter. It's been replaced by the BR to a register with a register, so that user programs no longer have access, direct access to the program counter. Okay.
Can you even read from the program counter at all?
You can, yes. Can't write to it. Okay, any questions? All right. Then we are going to continue talking about pipe and fork and exec. So where did we leave that? Last class. Anybody?
We were
program.
we were working on exec L and exec B, and we
Okay,
made a small program that gave us the parent and the child and printed out things.
okay. All right, well, let's write another program and then we'll write that again and we'll expand on it, okay? So you help me out here. Fork exec pipe CPP. Sure, I guess I'm doing it in C++. Uni std.h. Do I need standard lib if I'm doing it in C++? Don't think so. I'll find out soon. So, where we're going with this is we're going to run a program that, we're going to write a program that stands in place of LS. And all we want to be able to do is specify argv sub 1 would be the path of a program, no, sorry, the path to a directory for LS to do its business on. So we've got to make sure that we have an argv sub 1. If argc is less, what?
Sorry, I'm just like asking what would we want to be naming this specific program that we're copying from you?
I don't care.
You're mentioning that we're going to be using it for the next project, so.
No, no, no. We're going to expand on it today. This is an in-class effort. Okay. So if argc is less than 2, let's use our knowledge of standard error, so C error. And okay, so all we're going to do right now is, let's say, PID type PID equals fork. And what's that going to do?
That will get if it is a child or a parent.
Okay, so one process goes in, 2 processes come out, right? If the PID is 0, or another way of writing that, if not PID, then you are the child. And do I need anything here? I don't need an else. Yeah, so I don't need an else. Okay, so here you are the parent. All right, and let's clean that up a little bit. Let's say int ret val equals 0, and we'll return ret val. Okay. So why don't we say hello if we're in the child? So see out, hello from the child. And we'll say hello from the parent. And over here, just we wrote a little, let's test a little. So let's say exit. All right, let's see if we can get this to compile. And G++ and okay, so a.out. Please specify a command line argument. So here's a command line argument. Hello from the parent, hello from the child. Does anybody have questions? Okay. All right, now let's bring in exec. And which one did we use? I believe that we used exec, what, L?
We kind of used both, but we ended on I think we ended with I can't remember which one we ended with. We used both, but probably exec V.
All right, well, let me take a look at the man page. And man exec. And that's obviously, that's chapter 1. That's exec that's built into the shell. So man 2 exec. Nope, must be man 3 of exec. All right, so all right, looks like the easiest one to use will be exec L, because this is a trivial example. So that is a path to the program you're going to run, followed by whatever its argv0 is going to be, followed by whatever its argv1 is going to be, and then a null. Okay, no problems there. So exec L, and the program I want to run is just going to be very simple. This is going to run on Linux, right? /bin/ls. And this is going to be its argv0. So let's call it ls. And now we want its argv1, which is going to be our argv1, same thing. And then we got to give it a 0. Okay, and so there it works. A dot out, and I'm going to give it dot. And so it just exec bin/ls and fed it dot, and that's why I got an output of my current working directory. Okay, let's look at the code. You tell me if you have any questions.
Yeah, I think I have a quick one. Why does exec_l need a 0 again?
Okay, so remember back to when we studied argv. Let's go here. It needs the 0 because your argv is itself a pointer to an array, and the array must be null terminated. That 0 is that null terminator. Remember now?
Yeah, that makes sense.
In the
Okay.
code from last time, we used argv in order to get all the codes and whatnot that it wants to use.
Yeah, well, that was last time, and this time we're doing it this way.
Can you remind me what the difference is between XL and exec L and exec def?
Exec L versus its cousins.
Yeah.
Well, let's take a look. Okay. So exec L is it's a variadic, and I taught you about variadics. So this specifies the program you're going to exec, and then everything that comes after, including the 0, is going to be copied into a constructed argv. The next version, LE, takes the first 2 same arguments, and then you pass in a, oh, I see what the difference is. Okay, so exec LE is exactly the same as exec L, except you also get to specify environment variables. Now, environment variables are these. Okay, so environment variables is a handy way of setting up flags that any program can query. All right, now let's go back to the man. So exec LE allows you to specify the an environment variables set. LP, okay, so it's going to be like exec L. So star file. We'll have to read the description to see what the difference between LP and L is. Clearly, there is a difference in a pointer, but I see const char star, const char star. One says path, one says file, so I don't know what the difference is there. Exec V is you built argv yourself and passed it in. VP, again, I don't know what the difference is here. And V capital P. You're also specifying a search string. So that is here. So echo $path. This is the one that's built into your shell. So when you type in foo, when it says command not found, it says that because it couldn't find an executable foo here, and it couldn't find an executable foo here, nor here, nor here, nor here, nor here. Only when it exhausts your entire search path looking for the executable does it tell you that the executable is not found. All right, now let's look at the difference between I read the explanation and I still don't know what the difference is between these versions. Const char star, and this one is also const char star. So I don't know what the difference is.
It's probably how they search through the files to return something specific. I don't know.
I don't know.
I'm pretty sure XXCLP will copy the path variables or something. I remember
Okay,
looking this up at some point.
let's get back to our code. Okay, any questions about the code? Okay, so this program, as you see it here, is sort of like it's a contrived example of using fork and exec. And the program that we wrote simply stands in place ahead of /bin/ls. And it works only on one argument. Okay, are we good? All right, let's try this. Let's first of all, let's make sure it exists. Which word count /bin, user bin WC. Okay, that's what we're going to use. So let's change this. Wrong key again. What the? All right, I will. All right, I'll just do it myself. Exec L to /user bin WC and WC and 0. Let's see what happens.
So the XXCLP will, if you don't specify the first slash, it will search the path of the current environment for that command. So like
Okay,
if you just wrote WC
yeah,
and then you did a P, it would search whatever your current environment is
yeah,
for WC.
okay. Good, let's do that then. Let's do exec LP. I actually did know that, but couldn't remember it. Okay, so let's just do that. So the P is going to search your path. All right, let's try this. Okay. So I get an error. Does everybody else get an error? Jordan, what are you trying to say?
I do get an error. It was loading. Sorry.
Okay, let's look at the code again.
At least I'm reasonably certain that's what it does. I might be wrong. Maybe I'm reading it incorrectly.
Okay, no,
Did you have
the exec functioned properly, Cephas.
Oh, okay. So I was right.
Uh,
Ish.
So what's producing the error is WC. WC is saying, I have nothing to read.
Oh, nice.
Okay. So where is WC trying to get its input from,
Standard in.
right? And looking at this code, where is WC's standard in?
Wouldn't it just read from the same? Would it read from the same stream as the parent?
Right. Let's experiment. So how about we redirect the input from the parent? Look at that. It works. So A dot out, and I'm redirecting the input to the parent from that file. Okay. So now WC is happy because what we just did was exactly the same as that. WC is happy because it has something to read from.
I'm a bit confused on what WC is.
Word count.
Okay.
So,
would this work with piping?
well, that's exactly what this lesson is setting up.
Could you just do a pipe right now from something and then run A dot out with the shenanigans? Would that work? I'm not
What?
sure. No, could you pipe into the standard in of A dot out and then word count would actually get that? Because WC
No.
works with piping, doesn't it?
All
Or
right, so cat step.cpp pipe that to ./a.out, and it needs a command line argument.
so it does work.
Oh, okay.
That's what I was wondering.
Yes, right. It works because you've given. It works because WC's standard input is the same as A.out's standard input, and the cat has given it some data. Okay, so let me draw this. Okay, so here's A.out, and here's its open file table. So 0, 1, and 2. So standard in, out, error. Okay. So cat file piping that to A.out, and I gave it a garbage command line argument. So cat is over here, and it has an open file table. And cat's standard output is being connected via a pipe. There is the pipe symbol. This output is being connected to the input of A.out. Now, A.out does a fork, which means that here's the child of A.out. it has this as well, then this the child becomes WC, and its open file table is preserved. So the standard input to WC is the output of cat.
So is this where we're getting, like, this is basically an application of exec where we can write this complex program that's like, print out supposedly we could write a program that's like prints out the average word count or something, and we can pipe in a file automatically.
Well, we can do that with the shell, as I just demonstrated.
Yeah.
So cat, step, and I can pipe that directly to cat, WC.
What does cat do again? That's the
Cat just reads and dumps.
Oh yeah.
Read, print, read, print, read, print. Okay.
Has everybody seen the weird little pipe symbol before?
Binary or.
Yes, that's correct.
In this context, I mean.
Oddly enough, yes. I was working with a friend who goes to Gateway, and he was doing his homework and he was learning piping earlier this semester.
Okay.
No.
Okay. So now let's start using pipe. So look up pipe, man to pipe. So pipe takes as its argument an array of 2 ints. And it will return 2 file descriptors in that array. If there's an error, -1 is returned. Okay? All right. So in the parent, let's create the array. In the parent, before the fork, we'll populate the array. By creating the pipe. And we should check to see if the return value is bad. Yeah, I could just, yeah, exit. Wrong. Good deal. Not the world's best program. Okay, so now you've created the pipe. I wonder what those file descriptors will be. Anybody have a guess?
4 and 5.
0 and 1.
Close.
0 and
Definitely
1.
not 0 and 1. Let's take a
What?
look at our open file table.
Oh, it should be 3 and 4.
Because we start counting at 0.
Yeah, I was off by a bit.
Okay, so here's 0, 1, and 2. In, out, error, and then unused, etc. So opening a file and creating pipes will go through your table starting at 0 and will find the first unused. So I will bet you the return values of the file descriptors will be 3 and 4. So that was FDs is an array of 2 ints. So FDs 0 is going to be the read side of a pipe. FDs 1 is going to be the write side of a pipe. Why is it called a pipe as well? That's really what it is going to function as. Okay, so here's the pipe. And here is program 1, and here is program 2. This is the right side. So that is going to be FDs sub 1. Here is the read side. This is FDs sub 0. So you write to this, whatever you write here to file descriptor array index 1 will be read by the file descriptor array index 0. Okay, anybody have any questions about that?
Can you explain that again a little bit? I was kind of confused.
Okay, so a pipe really is named pipe because it really acts like a pipe. So a pipe connects 2 endpoints. The system call pipe returns to you 2 file descriptors in an array of int. Index 0 is the file descriptor corresponding to the read side of the pipe, and that would be this end. File descriptor 1 corresponds to the right side of the pipe, and that would be this end. Whatever is printed here into the right side is available for reading on the read side.
Is it possible to have both being the same file?
Or anything's possible. But is it correct? Not necessarily. All right, let's go back to our code here. So I've created a pipe. I've checked to make sure that the pipe was created because the return value is not negative. So then I do a fork. Now remember, the open file table is shared now between it's identical between the parent and the child. So if we want the parent to write something to the right side, so how about this? Write. Let's see, what are the arguments to write? There'll be a file descriptor. So FDs, and we want the right side. And how about we, C++ is going to complain if I just use a naked string. So I'll add that. Okay, so there's a C++ string. And over here, I'm going to do s.sc string, and then s.size. Okay, somebody tell me what I just wrote. What does it mean? And why did I do it that way?
Well,
Okay, I just used this.
You converted a C string to a file, a C++ style string to a C string, and then got the size
Right.
of it.
Yes. So I have a S is a C++ string. which I converted to a C string. And that's the size of the string. All right. Now, hello from the child. There's the exec. But let's do some rearranging now. I'm going to close standard input, or, okay. So I've closed standard input. And let's take a look at what I just did. All right, so in the child, we start out like this. STD in, out, air, and file descriptor 3 is the read side of the pipe. File descriptor 4 is the write side of the pipe. So what I'm going to do is close file descriptor 0. This is the child, remember? I want the child to read from the pipe. So I'm going to use another system call that you don't know about yet, but you will in a moment, to duplicate this file descriptor down to here so that the standard input becomes the read side of the pipe.
I have a quick question.
Yeah.
So you feed an array into the pipe function. If that array is empty, it'll automatically fill in this case 3, 4 to that array. But what if we have numbers in that array?
They'll be overwritten.
They'll be overwritten? Okay.
Mm-hmm. Now, if that's a problem, that's your problem. All right. So I've just closed in the child. I've closed file descriptor 0. And now I'm going to duplicate. I use that word on purpose. I'm going to duplicate the read side of the pipe. So that's in FDs, right? Because I have FD, even though I'm in the child, I still have a copy of all the variables created in the parent before the fork. So, and that is the read side. Okay, let's make sure I used dupe correctly. Yep, I did. Okay, I used the first version. All right, let's see what we get. All right, so I'll just replace that with 0 for now. I think that's in stdlib.h. Okay, so it looks like I got nothing. Let's see. Well, now that I know which way I'm going with this example, I'm going to get rid of the requirement to have a parameter. Now I wish I was using a screen editor. Okay. So let's see what I've got here. I've got a string. I create a pipe. The pipe is good. I do a fork. I'm into the child. I close standard input. And
You never
I do-
read it.
Huh?
You never read it.
Well, WC is supposed to read it.
Oh, that's okay.
Okay, well, I better, let me just put something in here that says, make sure I didn't, make sure the exec worked. Let's just make sure that's not the case. Okay, so it did do the exec. What the hell's going on here? This should be trivial for me.
I'm getting an
Don't know
error
why.
saying STD in was not declared in the scope.
Yeah, change that to
STD?
0. Change
Yeah.
STD into 0.
Let's see.
I remember this project from OS
stdlib.h.
being so annoying.
Okay, so stdlib.h, you should be able to use stdin now. Okay, where the hell is stdin? Man, stdin, I don't think that's even gonna work. I have forgotten where stdin lives. All right, how about this? Include
STDIO.
stdi, that's what I was just gonna add. So we don't need stdlib. What the hell? stdio.h, I wrote that. All right, I'm not gonna figure this out now. I'm just gonna use 0, all right? So read, write. Change the file descriptor for the child. All right.
Maybe you should try dup2, because I remember this project being super annoying, and sometimes dup2 worked while dup did not.
All right, so this is, it's gonna go from to.
I believe that's it.
And then this would go away.
Yes.
But that shouldn't make any difference.
Shouldn't.
Man to loop 2. Value of the new, okay. Which one is which? File descriptor 2? Okay, so I've got it backwards.
Wait, are you sure there's not a concurrency issue?
You know what? There might be. No, there isn't. There isn't.
But you're sure that write is going to happen before the exec?
But the pipe is open. The bytes will go sit in the pipe. And they'll sit there. Here's where the concurrency problem is. The pipe is being closed before WC can read it. That's the problem.
Why don't you write to it before you exec to make sure?
Yeah, it's the same thing is true. It would have closed. Come on. All right, well, now I'm confused.
Try
So-
just for my sanity's sake, could you remove the write up?
Here?
Yeah. Because WC is not actually complaining that there is a input
Yeah, it's
problem.
finding
So
an empty, it's finding an empty input.
it's just you're not putting anything in it. Hey, that worked, right? There are two of them anyway.
Yeah. I should have made them distinguishable. Okay, well, this lecture is going bad. And it's going bad. I mean, I know this stuff cold. I know this stuff like the back of my hand, yet I'm not having success right now, which is annoying.
It happens to the best of us, and the worst.
Interesting. It
What?
didn't say from the pipe.
Wait, why is it printing hello twice then?
Did I save this?
Wait. Look, see out. See out is writing to the same thing, isn't it? Or because when you actually write to see out, aren't you technically writing to the input section of it, and then the shell is spitting it out?
No.
He never touches file descriptor 1, which is cout.
All right,
Wait.
no, I've definitely written that.
Wait, does not see out write to FDS1?
No, of course not. It writes to file descriptor 1, not FD's 1.
Oh. But then
What the hell?
I remember doing our pipe project and I hated it strongly. Well, I don't know, I hate it. It was just very confusing.
All right. Well, let's blow off this one. I mean, I actually wrote this demo program yesterday and I had no trouble, so I'm forgetting something, obviously. So let me lecture a bit and we'll come back to this on Thursday. Terrible, terrible, terrible. Sorry about that. Okay. All right. So let's tap dance. So we have learned about fork and we have learned about exec, and we were in the process of learning about pipe. And a pipe is an example of an inter-process communications IPC. So IPC. An IPC is one method of communicating between processes. Now you use pipes natively in the shell by saying A piped to B. So what that will do is, if here is A's open file table, Yeah, I'll probably, yeah, all right. So 0, 1, 2, 3, 4. So writing, let's say from the standard output of A is going to go into the pipe. The pipe is going to dump its output into the input of B. So here is the standard in. Here is standard out. Okay, so the idea is when you run this, the shell will have created the pipe first, then arranged for a first child, namely A, what will become A. It arranges for the output of A to be connected to the input of B via the pipe. So that anything written by A to its standard output will show up at the standard input of B. Okay? So that is the idea of an IPC, being able to communicate from one process to another. There are other mechanisms for IPC. So some of the mechanisms for inter-process communication could be pipes, could be sockets. Okay, so this is networking. Okay, you could use shared memory. You could also use signals. So this is, but signals only convey events that happened. So either a signal occurred or it didn't occur.
I think I know your problem.
What?
I think you have to close the reading end first, right? Before you
Yeah,
write
there's
to
some
it.
closing that has to be done, but I wanted to demonstrate it. The reason why I didn't do the closing is because I wanted to demonstrate the error. But apparently I'm demonstrating the error better than I thought.
So I think if
So-
you close before you write, it should work.
All right, I'm willing to try that. Because this should not be here. It should be down here. And also, let's see, hello from the parent. And so in the parent, let's close the file descriptors. We're the parent, we're writing, we are not doing any reading.
Yeah, close that one.
Yeah. And that may be enough to make it work.
And then you still need that wait.
Hello from the parent. But where did the output from WC go? All right, well, this one is the child, and it will not be doing any writing to the pipe. So it can close one. And
Pipes are confusing, man.
that shouldn't be necessary. All right, now I've battened down all the hatches. This really should work.
Hey,
Now it does.
boys, let's go.
Okay. So got it to work. So I was demonstrating the error that I wanted to demonstrate. It didn't work. Okay. Now, all right, so now I'm going to comment this code so you can see what's going on.
Could you also put this code in the GitHub?
Yeah,
Sweet.
I'll put something better. I will write you a much more explanatory program. So the child, we want to move the read side of the pipe to the standard input of the child. Let me delete this, put it here, and document that. Okay. The child has no use for the right side of the pipe. This must be closed in order to assure correct operation. Okay, so this use of dupe 2 is essentially a move of the open file descriptors.
Why? I don't think we should have to close when we do DUP2 though, right? DUP2 should
Does it say that
automatically-
it closes it at the original location?
Yeah.
It does?
Yeah, yeah.
Okay, then we don't
Does.
need to close.
I think it made too many edits immediately. Because then we can't trace down what actually did it.
All right. So the read side and the write side in the child have now, as long as dupe 2 is going to do the close of the from file descriptor, then we're golden. Let's try this.
It says DUP2 makes new FD to be the copy of old FD, closing new FD first if necessary.
Yeah, that's not what we did here. So you do need to close.
But it seems to be working.
Yeah, for now. Okay. Now in the parent, the parent will do no reading from the pipe. So close its read side. This is write a string to the right side of the pipe. Entering EX mode. All right. Pipe visual. All right. Unless this is closed, the child will not receive an end of file. But of course, exiting the parent will close the file descriptor. So that's not such a big deal in this case.
So I'm kind of confused on why we close, like for the parent, why we close the read side. So I get it's not using it, but will it do anything bad if we don't close it?
Yes, it won't work. as we saw.
Why? Yeah. So why? I'm just confused. Why it won't work? Or is it one of those things we just kind of have to accept that it won't work if you don't close it?
Well, I'm gonna comment this out. And it does work.
Wait, close the one in the child side. Comments out the one on the child side. I'm reasonably certain you have to close one of them at least.
Yes. Okay. Now, the problem is WC won't print anything until it gets an end of file. That's the way WC works. It's counting the number of words, the number of lines. So it has to get an end of file before it prints anything. Now, it won't get an end of file as long as the parent has the right side open, as long as anybody has the right side open. So this is the right side of the pipe. Unless we close it, let me explain it a different way. Okay, at this moment, when we do the pipe, there's only one process. So that means only one process has the read side open, one process has the right side open. Okay? Now we're after the fork. We have two processes, so there are two read sides open and two right sides open. This is closing in the child, the right side. So now the right side is open only in one place, in the parent. That means when the parent closes its right side, the child will receive an end of file. Okay, so if this is not done, the child won't get an end of file. Okay, so that's critical. In order to get the end of file, there needs to be only one instance in which the right side is open. If there's more than one, then all of them have to be closed before the end of file is received. All right, so clearly I have to do a better job of demonstrating this. And I will do that by writing you a special purpose program to explain all this. Okay.
Wait, is our next project have something to do with this?
No. No, you did this in the OS class. That's where we'll do a project on pipes.
Oh, nice. I'm glad. Pipes were annoying. Are
Okay.
annoying.
So I guess speaking of projects, when do you think our project 7 is going to be assigned? Do you have an idea?
Well, probably by next week, if I assign one at all. So I'm gonna wait for emails from Thomas and Cephas and at least one other person pleading not to have any more projects. And then I'll choose. Because Thomas, remember last time, says you're not getting any rest.
Yeah. I said that we had very little downtime between projects.
We have 8 hours of downtime. That is good enough.
Mm-hmm.
I was
Okay.
honestly expecting it to be assigned this week.
Yeah.
The more we talk about this, the more nervous I get that he's gonna be like, well, I'm just gonna get it.
Well, I did a terrible demo. But the concept is straightforward. The idea of a pipe is it is a buffer in someone's memory. So inside someone's, let's talk more about pipes. So an infinite amount of data can pass through a pipe. But that doesn't mean that the capacity of a pipe is infinite. In particular, the capacity of a pipe, i.e. amount of data at once, is limited. And it's limited, in the old days, it was 4 kilobytes, which, excuse me, is now kebibytes. Okay, these days, it's probably 64 kilobytes or kebibytes. Kibibytes, that's it, kibibytes.
Gibbs.
Wait,
Okay.
why would it be kibibytes? Oh, I remember.
Because I'm being precise. I don't want anybody telling me that 4K, 4 kilobytes is 4,000 bytes, Jordan. I want you to know that it is kilo in binary, so it is kibibytes. There, with a capital B, not bits. We had this exchange on Facebook. All right, so at any given time, the pipe can become full. So there is a way of doing synchronization between processes. And that is actually the subject of the remainder of the term, is synchronization. Between threads and between processes. So where synchronization comes into play with pipes is, so let's say you were the writer, the right side of the pipe, you're the writer. You can write to the pipe until the pipe is full. And then you go to sleep. You become blocked. The next time you try to write to the pipe is full, there's no room in the pipe, so your process goes to sleep. Now the reader reads from the pipe, making room in it. If someone was sleeping on the right side, wake them up. If the reader has read all from the pipe, it's drained the pipe, then it goes to sleep. Which means there's one thing left out up here. Okay, so when you write to the pipe, wake up a sleeping reader. Okay, so the synchronization takes place on the read side and on the write side. So the writer gets put to sleep if it ever fills the pipe, and it will be reawakened when there is room in the pipe to write some more. A reader that attempts to read from an empty pipe will go to sleep and will be reawakened when something is in the pipe for it to read. They're reciprocal. Okay, so the reader attempts to, let's talk about the reader only. The reader starts running and it reads from the pipe. There's nothing in the pipe, so it goes to sleep. Later, the writer comes along and writes something to the pipe. That causes the reader to wake up and will drain that information from the pipe. If the writer at the same time is not continuously writing, it means that the reader will catch up and find itself draining the entire pipe again and go to sleep. So the amount of data that goes through a pipe is infinite, but it's only, let's say, 64 kebibytes at a time. Okay? Now, in the shell, you can actually demonstrate this, but I'm not going to take any chances. The class is almost over. Barbecue on Thursday, yes. Okay, questions about pipes? Let me look at something. Oh, yeah. Okay, so let's see what we got here. I have no idea what I'm looking at, but let's see if it's worth anything. Make. Okay, so. All right, this isn't going to demonstrate very well, but this is going to be a project for OS in the fall. You're going to create your own pipe. You're going to actually implement pipes. Okay? Now, did I put, what I'm wondering is, did I put that in the summer stuff? Is it already online for you? Anybody see? Okay, summer, that's what I wanted to see. Cat P1.md, no, head. Okay, so here you're going to write your own shell. Yeah, okay. Yeah, so, and the project is already online. You can start writing your own pipe over the summer. By the way, you are able to ask me questions over the summer. So look at this. You've got 1, 2, 3, 4, 5 total projects. If you do these over the summer, you'll have very little work to do during the fall term in OS. Let's see this, when you took OS, did you do any of them over the summer?
I did the pipes one, which was the first one we had to do.
Or would that be P1?
I believe so.
Okay.
I don't know if this is the same though. Because the
Yeah.
pipes one we did, we didn't make a pipe. We like
Yeah, that
did
was
some
P2.
inter-process communication thing.
Right. Okay, so review then. You know what fork does, you know what exec does, you know what all of its cousins do. You know that pipe is an interprocess communication primitive. There's a read side of the pipe, there's a write side to the pipe. In order for pipes to function correctly, you have to do the bookkeeping. There should only be one open read side. There should only be one open to the right side. Otherwise, things get messed up. You know that a pipe has infinite throughput, but finite capacity. So when the pipe reaches its full capacity, the writer goes to sleep, waiting for room in the pipe to continue writing. When the reader has drained all the information from the pipe, it will go to sleep, waiting for there to be something else to read. So the synchronization takes place on both sides. All right, any questions?
So in like the pipe situation, let's say we have an odd amount of bytes causing the next section not to fit completely. So would the pipe recognize that it's not big enough to fit? So would it would it go to sleep, or would it do something else?
Yeah, all of the bytes up to the very last byte to fill the pipe would be written, and then the writer would go to sleep in the middle of its writing. And the writing would resume when room was made in the pipe. I think I understood your question.
Yeah, that's what I was asking.
Right. Jarrett, do you have any questions?
So the reader creates more space to write. Am I
Exactly. Yeah.
correctly?
Hey, you remember we talked about circular cues?
Yeah.
A pipe is another example of a circular buffer.
So
The reader, go ahead.
it can infinitely, like it can keep writing more and more.
Yeah, the amount of data that can flow through the pipe is infinite, but the circular buffer has a specific capacity. Let's say 64 kebibytes. Right? So if the reader is slower than the writer, the circular buffer, the pipe, will fill up.
Okay.
When the pipe fills up, the writer has to be paused so that the contents in the pipe isn't overrun. The reader has to read in order to make room in the pipe. So the reader drains from the circular buffer.
That makes sense.
If the reader is faster than the writer will get to a point where it has drained the contents of the pipe. So the reader must be paused until there's more to read. By the way, this is a big deal concept. It even has its own name. What we're talking about is a producer consumer. So this is the right side. This is the read side. So a pipe is actually an implementation, yet another implementation of a circular buffer. And a producer fills the pipe, the consumer drains the pipe. And there's synchronization between them. Meadow, do you have any questions?
Nothing specifically right now.
Okay, please reach out to me. Everybody is welcome to reach out to me to work on previously assigned projects, okay? I want to see no Fs in this class. So if you have a project that you didn't do, you can come back and do it. If you don't have, if you did do it, you don't have the grade that you'd like, you can go back and resubmit it. Just let me know. You can get help from me to resubmit. Joshua, you have any questions?
Nope. Yeah, I'm good.
Morgan?
No.
Okay. And Jacob, how about you?
I'm still so surprised
I'm all good.
that there's not that many people actually engaging in the voice chat. Like of the people in the class, not everyone shows up is what I'm referring to.
I don't know what to say about that. It's unfortunate.
Do you mean on like the Discord?
Yeah, like all the people that I believe signed up for the class aren't really showing up.
I don't think that's really much of our business to really.
Yeah. I mean, I know, I'm just surprised, that's all.
Okay, so I'll see you on Thursday. You got to get in your project 6. It was due last week, right?
Yes.
Okay, so get your project 6 in. And if you want to help on any of the projects, let me know. All right, class is over. I owe you a better documented example. Okay, bye-bye.